Hey, chemistry, this is Thursday, May 7th. Good to be with you again. We're going to be doing titration. See the gloves? Okay, I've got my gloves. See the goggles? Yep, got my goggles. Okay, I'll just put them over here. And if you ever get some of this acid that has been watered down tremendously for my labs, 1/10 molar concentrations of sodium hydroxide, 1/10 molar sodium of hydrochloric acid. If you get it on your hands, it's not going to hurt you. But after every lab, you want to wash your hands with soap and water at the sink and just get them rinsed off really good. All right. So we're going to go ahead and we're going to set up for a lab. This is a burette. I've got a stopcock right down here. That's a twisty thing. Over here, I have a burette that has a pinch cock. That's another little twist. Well, it isn't a twisty. It's a squeezy thing. It's a pinch cock. Stopcock, pinch cock. And what I do is I pour in. You'll notice that my funnels have these little places that allow the air to go down there. So you can, but you still might want to raise it up while you're pouring it in. We're going to go ahead and use the 1/10 molar sodium hydroxide as our standard. We call it a Titrant Standard. And I'm going to go ahead and put it in. I'm going to make sure that this is closed. That's perpendicular to the burette. And I'm going to go ahead and put some in there. As you know, if it's open, it will just simply pour onto the ground. Okay, that's nice. And we'll go ahead. And when you get to your lab in college, you'll see a little dust cover on there. That keeps the water from evaporating so much, and it keeps the dust from getting in there and contaminating your solution. This is called the Titrant Standard because we're going to use it as the known. The known what? Known concentration. We know it's 1/10 molar. I told you this is 1/10 molar hydrochloric acid, but you're not going to know that. That's unknown. We're going to try to come up with that molarity. That's the whole purpose of this lab. Okay. So first of all, we're going to go ahead and we're going to draw out some hydrochloric acid. You can either use, one of these, what's called a graduated cylinder, or you can go ahead and use this because its neck is, because it is a narrower thing, it is more precise than the little marks on here. Let's say we draw out 15 milliliters of acid. We know how much acid we're starting with, 15 milliliters. There you go, bottom of the curvature, which is called the meniscus. Perfectly, 15 milliliters. Okay, so we're going to go ahead and pour that into the Florence, the Erlenmeyer flask. You always use Erlenmeyer flasks. If you ever watch lab rats on TV, like Crime Scene Investigation or whatever, they're always going to use these things. They're not going to be using, these kind of things like a beaker. They're going to use this because it's always been done that way. And so what we're going to do, don't forget, we got to put in an indicator so that we know when it's turned, when it's the chemically equivalent amount. So we're going to go ahead and put, 5 or 6 or 7, 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's good enough. Drops phenolphthalein indicator. And if you look on page 5, let's go look on page 513 to refresh our memory. 513, phenolphthalein indicator is pink at the transition point. Say transition point, say equivalence point, say end point. That's what it's called. And we're not going to want it to go into the dark pink. We're going to want it to be light pink, and we're going to stop right there, the end point of titration. Okay, so then let's go over to page 519. You see on 518, 519, that's what we're doing right now. And then we're going to do the calculations on page 520, like sample problem F. Okay, so here we go. So I'm going to go ahead and twist this thing. So what do you have this here for? But this is my little deal. Now, what I like to do is I like to, let me adjust this just a little bit. I like to swirl with my right hand and turn with my left. Can you tap your tummy and tap your head, swirl on your tummy and tap your head at the same time? You know, it's hard, but that's what this is all about. We're swirling it because you know one drop can change that dramatically. So we got to be careful when we drop in. I put a lot in initially, and then when I wait and I see a little pink appearing, then I go ahead and slow her down to a drop, drop, drop. Okay, next thing. I'm going to go ahead and got my phenolphthalein in there. What was I going to do? Come on. I was going to write down my starting point. If I don't write down my starting point, I got to do it all over again. So you read the burette. Up here on the burette, it says 0, then it says 1, then it says 2, then it says 3. So it gets bigger as you go down all the way to 50. So I've got to read it right here. So it says 22 right there. And it says 23 down there. And the water is right in between. It's not the water, it's the base, sodium hydroxide. And it says 22.3. So it starts 22.3 milliliters. That just means that I have 22.3 milliliters of the stuff in there. Look, there's one thing I forgot to do. I forgot to prime this thing. So let's get some of that going through first. Okay, now we're ready to go. Okay, it says 23.6. It gets bigger as you go down. So I'm going to go 23.6. You see that? Yeah, I think so. All right, so let's go ahead and titrate. Here we go. I'm going to go ahead and twist this thing. You can see that it's coming out, maybe. I don't know. See it when it hits, it turns pink, lavender, but I swirl it right out. So I have not reached the end point yet. So we're going to keep going. I'll give you a hint. Since this one works out 23, 33, 38. It's going to be around 38. I just happen to know that. So I'm going to go fast because I don't have that much time. So it's passing 33 right now. I'm swirling it out, so I haven't reached the end point yet. I kind of have an idea of when it's going to hit. It's going to hit around 38. When you've done enough of these, you know what you're aiming for. Keep swirling. Slow down. Okay, here it goes. Drop, drop, drop. I'm drop, drop, dropping now. Here it goes. Oh, I overshot it. Man, I got too excited. Do you see that? It isn't light pink, it's dark pink. So I'm gonna have a little error there. It reads 36.5. It gets bigger as you go down. 36.5. So we started when it read 23.6, and now it reads 36.5. So subtract them. When you subtract them, what do you get? You get about, let's just call that 0.6. Okay, you're going to get 13 milliliters. That's how many milliliters of the NaOH it took to neutralize the acid. So what did I start out with? I started out with a volume of 15 milliliters of acid. And the concentration, unknown concentration. I'm going to go ahead and put down molarity is unknown. And I have this burette. And in the burette, I used 13 milliliters. And the concentration was 0.1 molar. Okay, so in this case, we've got the molarity and we've got the volume. In this case, we've got the volume, but we don't know the molarity. That's the process we're going to have to use to figure this out. This is sodium hydroxide. That's our Titrant Standard. And this is hydrochloric acid. And so that's the unknown. The Titrant Standard on the top, the unknown on the bottom. So what we say is, this happens, they both happen to be strong. That's a strong acid being titrated with a strong base. Say that with me. A strong acid being titrated with a strong base. Let's do the balanced chemical equation. Hydrochloric acid, let me put this out of the way here. Hydrochloric acid plus sodium hydroxide yields NaCl, that's the salt, and water. I've already done this once, balancing it. I know it needs a 2 right there. Step 1. Calculate the moles of the known. What's known? This is called the known. The one that has 2 things given. So the moles of the known. How do you do that? Molarity is moles over liters. Remember that? So the molarity is 0.1. And that equals the moles. And we're going to divide by 1,000. 0.013. 1, 2, 3 bunny hops would be 0.013 liters. Okay, so now the question is, do you know how to cross multiply? In order to get the moles, that would be that times that. I can do this in my head. 1/10 of that is going to be 0.0013 moles of HCl. No, NaOH. You remember where moles go? Moles go underneath. Grams go on top, moles go underneath. We're going to do some stoichiometry. Stoichiometry. That's step 2. Okay, so 0.0013. What are the coefficients? Aren't the coefficients 1 and 1 and 1 and 2? So let's go ahead. If it is a 1-to-1 relationship, can I do my stoichiometry in my head? 0.0013 moles of that gets neutralized with 0.0013 moles of that. Yeah. So now we know moles. So now we're ready to do step 3. Step 3 is to calculate the molarity of the unknown. Molarity of the unknown. So that's the formula. The formula is molarity is moles over liters. This time we're calculating not moles. We did moles with this before. This time we're calculating molarity. This time it was with NaOH. And this time down here it's going to be HCl. We're going to calculate the molarity because we know the moles is 0.0013. And the liters that we started with was 15 milliliters, 0.015, 3 bunny hops to the left, 0.015 liters. So moles over liters. Moles from up here because we did this stoichiometry, and liters down here because we knew we drew out 15 milliliters of it to begin with. Okay, so what am I going to do? I'm going to get my calculator. I'm going to get my calculator, and I'm going to do this. Okay, we're going to do 0.0013 divided by 0.0015. No, 0.015. And it goes 0.087. With a capital M there for molarity. That is the unknown molarity of the hydrochloric acid, 0.087. What did I tell you that it was when we mixed it in the laboratory? Didn't I say that I had 0.1 molar hydrochloric acid here? So 0.087 is either because you did bad titration, and I think I did because I overshot it. And then secondly, I could have mixed it poorly. Let's find out what the experimental error is, and then I'll let you go. The experimental error works like this. You put down what you got, .087 molar, minus what you should have gotten, over what you should have gotten. And you multiply it times 100 for the privilege of hooking on a percent sign. So let's do that. Minus 0.1 equals divided by 0.1 equals times 100. And I get 13.3%. Negative experimental error is negative 13.3%. That means it was below what I should have had. 0.087 is below 0.100. 87 thousandths is below 100 thousandths. Okay, so 13% error is not that bad. See ya.